Hello everyone, welcome to UnQuestionIt. In this video series, I'll be making videos for competitive exams, specifically for physics. I intend to cover each topic syllabus wise so that we don't miss anything. Stay tuned to my channel. If you like the video, then please subscribe the channel for more videos coming down the pipeline. So, let's get started. Today's topic is vector algebra. So we'll be covering three topics in vector algebra. The first one is vector operations. The second one is vector algebra component form. And the third one is the triple products. Vector operations. So before moving to the vector operations, let's see what are the vectors. So any vector is a combination of one scalar quantity and a direction added to that. So it has the information of that scalar quantity and direction in which that scalar quantity is being applied. So let's say here is the car and it is moving with 5 meter per second. 5 meter per second. This information is itself not sufficient to say that where the car is moving. So you'll have to say that okay, so this car is moving in the plus x direction with 5 meter per second. That is the information which you require to make it properly explainable. Okay, so the examples are velocity. Now whatever the quantities are described by these velocities are also vectors, like acceleration. So acceleration is equals to dv by dt. So the change of rate of velocity. Okay, so this will also be a vector. Force equals to mass into acceleration. So since mass is a vector, since acceleration is a vector quantity, the force also will be a vector quantity. Okay. Momentum. So momentum is a multiplication of mass into velocity. So you see that momentum will also be a vector quantity. So the vector quantity has a direction and a magnitude. Okay, and any quantity which is also derived from vector quantity is also a vector quantity, like these you have seen here. Okay, so how do we denote a vector? So a vector is denoted by some letter, let's say velocity in this case, and a arrow on top of that. So this is the notation of vector we'll be using. Some people also use the notation with just a bar, but we'll be following this notation. So you can see this one or this one, whichever one you see, that defines a vector. Okay, so what are the operations we can do on vectors? So the first one is the addition of two vectors. So these are the algebras: addition, multiplication, subtraction, like that. So the first one is the addition of two vectors. So suppose that you have given a vector A and you are given a vector B. So the summation will be, you make a parallelogram out of it, and this diagonal will be your summation of those two vectors. This is the summation of the vector A and vector B. In other way, you can also look this problem as, okay, so let me draw the vector A here. This is a vector A. You can take this vector B and put it here. So because you will not going to change the magnitude of it, and you are not going to change the direction of it, you are just taking it and putting it here. So now this is a vector A. I am going to put the vector B here. Okay, so this is now vector B. So the addition of that will be this vector A plus B, this line, which is equivalent to this line. So this is called the triangle rule of vector summation. Okay, so now we have the information how to add two vectors. So now we know that how to add two vectors. If now somebody asks, instead of adding two vectors, I want to subtract two vectors, that is, I want to calculate vector A minus vector B. So let's see how to do that. So let me draw exactly the same thing. So we have a vector A here. We had a vector B there, which was vector B. And what is the negative of this vector B will be this vector. This vector will be negative of vector B. So if we take this vector and put this vector here, so this will be minus vector B. This was vector A. Okay. So what is the summation of these two? So you take this and go till here. This will be your vector A minus vector B. Okay. This is the same as the triangle rule which we saw here. So instead of adding vector A and vector B, now we are adding vector A and minus vector B, which gives us the A minus B, which is equivalent to the subtraction of the two vectors. Fine. So the next one comes is the multiplication of a vector by a scalar quantity. So let's say you are given a vector A. Okay, and you want to multiply it some factor. So let me draw a vector A here. This is vector A and I want to multiply it by 2. So how this vector will start to look? It will be vector A, the original one, with the same direction but with the double in the magnitude. So this is the double of the magnitude of vector A. So this will be 2 vector A. The direction will be exactly the same, parallel to vector A. So this is how we multiply a vector by a scalar. The magnitude just scales, the directions remains the same. So this is distributive in nature. So suppose that you are given a two vectors with the summation. So you are given vector A plus B, and if you want to multiply it with a scalar A, it will be vector A multiplied, it will be scalar A multiplied by vector A plus scalar A multiplied by vector B. So this is the multiplication of a scalar quantity with a vector. So the next property we have is dot product of two vectors. So dot product is very important one because it is being applicable to many cases. So let's see. Let's say you are given a vector A and you are given vector B, and the angle between them is theta. So their dot product A dot B, dot product is being represented by dot there. So A dot B equals to magnitude of A into magnitude of B into the angle between those two, the cosine of those. So we normally write mod of vector A as A, so without mod and the direction or the arrow. So same as B, then cosine of theta. So the dot product of vector A and B is AB cos theta. Okay. So some properties of it. So it is commutative. So that is A dot B equals to B dot A. That you can also see. If you put B dot A, you will get BA cos theta, that is same as AB cos theta. It is also distributive in nature. Distributive, that is, if you take a dot product of some vector with the summation of two vectors, you will get dot product of these two plus summation of dot product of these two, that is A dot B with the first one plus A dot C with the second one. Okay. One thing to note is that the dot product is scalar in nature because the vector signs from both A and B got removed in the operation of dot product. So this is a scalar quantity now. Okay. So now we have a cos theta there. So we have 1 degree of freedom with which we can play with. So suppose if this angle is 90 degree, so if vector A is perpendicular to vector B, so their dot product A dot B will be AB cos 90 degree, that is equals to AB into 0 equals to 0, because cos 90 is 0, you will get 0. So if two vectors are orthogonal or make 90 degrees with each other, their dot product is 0. The other case is when vector A is parallel to vector B, their dot product equals to AB cos 0 degree. So cos 0 degree is 1, so you will get A into B. So just the multiplication of their magnitudes. So if they are parallel, you can just directly multiply their magnitudes to get the dot product. Okay. So the next operation we have is the cross product of two vectors. So let me draw it. Suppose you have vector A and you have vector B, vector A, vector B. So their cross product A cross B is defined as mod of A mod of B sin theta into n cap. So let's see what this describes. So this n cap, what is n cap? So n cap is the direction of this A cross B. How do we get this direction? So this n cap is perpendicular to A as well as perpendicular to B. The other way to say is that it is perpendicular to the plane formed by A and B. So let's say this is the parallelogram which is formed by A vector and B vector. So A cross B represents this area with the direction perpendicular coming out of this plane. So it is coming out of this plane. Fine. And how do you get that direction? It can be into the plane and out of the plane also. For that we have the palm rule or the thumb rule. You take your right hand, put your hand in the direction of this vector A so that your palm face the other vector, and you make a rotation and you see your direction of the thumb. So in this case, if you put your palm here and try to rotate your hand in this direction, your thumb will say outward of the plane. So this n will be in this case outward of the plane. Now if somebody asks to calculate B cross A, so it will be B A sin theta into n cap prime. Why prime? Because this will not be same as n cap. Why? Let's see. Now take the right hand, put it in this direction, making sure that palm is facing this side, and make a rotation with your hand in this direction. You will see that your thumb is facing inside the plane rather than outside the plane, which was the older case. So this will be in the direction of inside of the plane. So the cross product is sensitive to the order we put for calculating the cross product. So in that case, the A cross B is not equals to B cross A, but A cross B equals to minus B cross A. So this n cap prime, that means n cap prime is equals to minus of n cap. So this is outward the plane, this is inward the plane. Fine. So this tells directly that the cross product is not commutative in nature. It's not commutative in nature, but it's distributive. What that means that if you take a cross product of A with B plus C, you will get A cross B plus A cross C. Okay, so the cross product is distributive in nature but not commutative. The interpretation of A cross B is this represents area formed by parallelogram by vector A and vector B. Okay, so this area is represented by A cross B, or if you don't want to take the direction, take the mod of that. Fine. So this is all about the operations of the vectors. In the next one we are going to see the vector in the component forms. So now the vector algebra in component form. Earlier section we discussed that vector has a direction and a magnitude. So we are going to break that into more granular form. First let's see, we have a coordinate system. Okay, we have X, we have Y, we have Z. So anything is moving in this direction, we'll say that it's moving in Y cap, or in some places you'll also see J cap. Anything moving in this direction is being represented by X cap, or in some cases I cap. Anything moving in this direction is represented by Z cap, or in some cases K cap. Okay, so if we have the coordinate system Z, Y and X, and we are given a vector, a 3D vector in the XYZ plane, a vector A. Okay, so it will have a projection in the XY plane, and this will be the height of that. Okay, the height of that. So this will be a, so since this line is parallel to y, this will be ay. This line is parallel to x, this will be ax, and this line is parallel to z direction, this will be az. So this vector can be represented as ax x cap, because it's in the x direction, ax in x cap direction, plus ay in y cap direction, plus az in z cap direction. This is the dissociated form of a vector in the coordinate system. Okay, so this form is very helpful, as we'll be see in the upcoming examples. So associated with this form, we have several rules. So rule number 1 is to add vectors, add like components. By that I mean, if you want to add a vector A and vector B, you write it in the component form: ax x cap plus ay y cap plus az z cap plus bx x cap plus by y cap plus bz z cap. Now what we can do is we can take x cap common and then y cap and z cap common. So it will be ax plus bx x cap plus ay plus by y cap plus az plus bz z cap. So you see, this can be separated into the different components and with the direction same as both ax and bx, like we have x direction there. This is the first rule. The second one is if you want to add this vector by some scalar quantity. That is, you are given a vector A, that is ax x cap plus ay y cap plus az z cap, and if you want to multiply it with some scalar A, it will be ax x cap plus ay y cap plus az z cap. That is, you can multiply that scalar with each component of that vector. Okay, now the next one is, okay, so the next one is, the third one is, if you want to multiply a vector with the dot product notation that we have seen. So the third rule, if you want to take the dot product of the two, so we have the same ax x cap plus ay y cap az z cap dot product with bx x cap plus by y cap plus bz z cap. Now this will be like normal multiplication, but most of the terms will be 0, because the dot product of perpendicular vectors are 0. So x cap is perpendicular to y cap is perpendicular to x cap, and that was the same thing. So y cap is perpendicular to z cap and z cap is perpendicular to x cap. So any dot of them will be 0. So any dot product of them will be 0. Okay, so all those cross multiplication, like if you are going to multiply ax x cap with bx y cap, that will be 0. If you want to multiply ax x cap with bz z cap, that will be 0. The only term which remains is ax x cap into bx x cap, and we know the property that if though the two vectors are parallel, their multiplication is the direct multiplication of their magnitudes. So in this case, the magnitude of unit vector is 1, so 1 into 1 is 1. So we'll have here is ax bx plus ay by plus az bz. This is a simple dot product of two vectors in the component form. Okay. The fourth one we have is to calculate the cross product. So we'll see what determinant form we are talking about. So cross product. So we have A cross B. Okay. So we can write it in the same form like ax x cap plus ay y cap plus az z cap cross product with the same bx x cap plus by y cap plus bz z cap. Instead we are going to write it as ax ay az bx by bz and the unit vectors in this direction. So this is the cross product is essentially can be written in the determinant form with the unit vectors on top of that, and the first vector component is on the second and the second vector component is on the third row. So if you multiply it, you will get, so let's take this x component there. So you will get ax bz minus bx az, ax bz minus bx az plus y cap. So let's take this y cap. So we'll get bx az minus ax bz plus for the z direction, if we take this one, so it will be ax by minus bx ay. This is the cross product of two vectors in the component form. So so you see that since we have the associated x cap, y cap and z cap there, the cross product is a vector. Okay, so let's see some examples. So if we want to find the angle between the face diagonal of the cube. So what is a face diagonal? So first let's draw a cube. So here is our coordinate system. Okay, to make a cube, let's do this. Okay, let's make it parallel to this, drop it here, make parallel to this and drop it there. So you can make a complete cube, but I am going to calculate the diagonal of the face diagonal of the cube. So what is the face diagonal? So this is a face, so its diagonal is this one, so its diagonal is this one, and we want to calculate the angle between those two, that is the theta. Okay, so this is one vector, this is the second vector. So if we say this is vector A and this is vector B, so essentially what we are going to do is calculate vector A dot B, that is AB cos theta. Okay, or so from there we can get the theta value, but before that let's calculate what are the vector A and vector B. So let's say this is the z direction, this is the y direction, this is the x direction, and each direction has a unit length. So this will be 0 0 1, this will be 1 0 0, this will be 0 1 0. Okay, so what is the vector a? So vector a is in the z and y plane. So it will be 1 unit in y direction and 1 unit in z direction. So vector a is 1 unit in y direction plus 1 unit in z direction. Okay, what is vector b? Vector b will be, so it is in z and x plane, so it is 1 unit in x direction and 1 unit in z direction. 1 unit in x, 1 unit in z. So b will be 1 into x plus 1 into z. So what is their dot product? Equals to let's write y plus z dot x plus z. So y into x is 0, y into z is 0, z into x is 0, z into z equals to 1. So we have 3 zeros and 1, which is equals to 1. So their dot product is 1. Now we have a dot b equals to ab cos theta. So what is a? A is y plus z. So what's the mod of that vector? It's under root ax square, or in this case ay square plus az square, equals to under root. So ay is 1 and az is 1, so 1 plus 1 equals to root 2, and mod of b is also the same. So in this case bx square plus bz square equals to under root 1 plus 1, that is under root 2. So we have, if we apply this formula, we have 1 equals to root 2 into root 2 cos theta, or cos theta equals to 1 by 2, or theta equals to 60 degrees. So we have the angle between the two face diagonals of a cube. So here you can see that by using the vector operations, we can easily calculate a lot of important quantities, which is actually very difficult if you want to do it by the measurement. Okay, so our next example is the find the component of unit vector n cap perpendicular to the plane shown in figure. So let me first draw the figure. So let me draw the coordinate axis x, y, z, and this is the plane formed by that. Okay, so let's see, this is 3 in this z unit, 1 in the x unit, and 2 in the y unit. So we want to calculate the unit vector coming out of this plane. Okay, so how can we do that? So if I say this and these are two vectors, so let's say this is vector A and this is vector B. So their cross product, if you take the right hand thumb rule, it will be coming out of that plane. So if you calculate A cross B, that will be magnitude of A cross B into direction of that A cross B. Okay, so we want to calculate n cap. N cap will be A cross B divided by magnitude of A cross B. So let's calculate what is A cross B. So first, what is vector A? Vector A equals to, let's see, so this and this, so this point and this point. So we are going 1 in the negative x and 2 in the positive y. So it will be minus x cap plus 2y cap. Okay. What is vector B? So vector B is formed by this point and this point. So we are going 1x in the negative direction and 3z in the positive direction. So it will be minus x cap plus 3z cap. Okay. So now if you calculate A cross B, it will be, let's make it in the determinant form, x cap, y cap, z cap. What is Ax? Minus 1, Ay is 2, Az is 0. What is Bx is minus 1, By is 0, Bz is 3. And let's calculate. So if we take x cap, we'll get 6. So it is 6x cap plus, if we take y cap, we'll get 3 there, plus if we take z cap, we'll get this minus this, so that is 2z cap. Okay. And what is the magnitude of that? That will be under root this square plus this square plus this square, that is 36 plus 9 plus 4, that is under root, let's see how much, 49, that is 7. So the n cap will be 6x cap plus 3y cap plus 2z cap divided by 7. That is the direction of the unit vector. Okay. So you see the power of using vectors to calculate the directions, to calculate the angle between the two lines. This can be done very easily. So the next one we have is the triple products. So what is a triple product? So now we have seen that vector A cross vector B was a vector. Okay. So we are going to apply the third vector on this one in the form of the cross product and dot product. Those two are the sub part of the triple products. Okay. So let's see the first one, the scalar triple product. So scalar triple product is defined by, let's say we have B cross C, two vectors, the cross product of that. Since this is vector, we can take a dot product of another vector with that. Okay. This is called the scalar triple product. Why scalar triple product? Because you see, this will give you a vector. This is also a vector. And if you take the dot product of that, you will get scalar. So this is scalar triple product because it gives you scalar. Okay. So how to calculate that? So we already have seen how if we have B cross C, we can write it as x cap here, y cap here, z cap here, and bx, by, bz, cx, cy, cz. I haven't written this x cap, y cap, z cap intentionally because I am going to fill it up. So if we take the dot product it with A, the components of A will be filled here. So ax, ay, az. This is the scalar triple product. So this is simply the determinant of the component of all the three vectors. So it's very easy to calculate. This is also true in the form of permutation. They are actually equal. So if you write A dot B cross C, which also will be equals to B dot C cross A, which also will be equals to C dot A cross B. Okay, this essentially comes from the property of the determinant, so you can take the permutation of it and the determinant will be same. So that goes same with the scalar triple product. So what is the interpretation of the scalar triple product? So we have seen that if we have given vector B and vector C, so their cross product represents the area formed by the parallelogram. If we have the another vector A here, and if we make the parallel part by this, okay, so if we make this, so A dot B cross C represents the volume occupied by these three vectors. So this whole volume is equals to A dot B cross C. So this B cross C represents the area, and if you take the dot product of another vector, that represents the volume occupied by those three vectors. Okay. The next one we have, and the last one, is vector triple product. So we have vector B cross C as a cross product, and if we take another vector and take the cross product of that, that gives us the vector triple product. So since this is a vector, A cross vector A is also a vector, their cross product will be vector. So let me write it down. So this is vector, this is also vector, and their cross product will be vector. Okay, so this is called the vector triple product. So their formula to calculate is, so it's not that straightforward. So you first have to calculate B cross C, and then the output vector you have to apply the cross product of A on top of that to get the another cross product of the vector triple product. So let's see the direct formula of that. So to calculate A cross B cross C, you can write it as, so you just take the B first, you write down the B, and then the dot product of A with C, minus you take the C and the dot product of other two, A dot B. So yeah, so this is the formula for the cross product or the vector triple product. In this section we have covered the vector operations, vectors in the component form, and vector triple products. So that's all for this video. Hope you like the video. If you like the video, hit like and please subscribe to my channel for the upcoming video.